All right. Now we're going to take what we've been talking about as far as electric fields and point charges that cause them moving into continuous charge distributions. And now we've moved up to actually applying this. So we're going to take this idea of a continuous charge distribution and use it in an application and actually look at capacitors. Right. So not a lot here. Just four topics. One of these is huge. This first one, 2.3.1. There's a lot of math in here. We're going to walk through another derivation of a continuous charge distribution and then use that toward understanding these parallel plate capacitors. So first of all, what exactly is a parallel plate capacitor? And the name sort of suggests exactly what it is. It's essentially just two plates that are perfectly aligned with each other. They're both conductors, so they can hold a charge. A charge will spread out on them. Um, and the idea is that when you have these two plates, they are charged equally, but oppositely. So you can see that here in the picture, we have a plus Q and a negative Q. That means if we were to sort of sum up all the charges on a capacitor, the net charge is going to be zero because while we have a positive Q, we also have that negative Q. So you're going to get those two canceling out. Now, because opposite charges attract, all the charge is on the inner surface of the two plates, which makes sense. We've talked about how charges distributed across conductors will sort of still be attracted and move to where they need to be to sort of find that equilibrium point. So obviously, there's no equilibrium point here because they're not interacting with each other. They just want to get really close because one side's positive, one side's negative, and they're going to keep trying to do that. Well, I guess I should say there's no equilibrium really across these surfaces because you're going to get charge sort of bulked up on the inner surfaces, not the outside. All right. So what is the electric field a distance z away from a parallel plate of a parallel plate capacitor? So if we have two of these, right, we're only going to think about the electric field right now from one of them. So the trick to do this, the way that sort of makes the most sense, and plus capacitors are actually, a lot of them are disc shaped, but there's also lots of other shapes. So let's think about this in terms of a disc, just like in our last example. We're only going to look at one of them though, not both of them together. So we have a symmetry argument that can be made. Okay. What we can do is we can actually say that the E field components in the radial direction cancel out. So anything pointing out away from the z-axis is going to cancel out. And we can see that over here. So what we're going to do is use techniques from Calculus 2, where we find the area of this disk, but we're going to add up thin rings to do it, okay? So essentially, we're just going to add the contributions of individual rings across the surface. And now, if you look over here, we can see that we have this ring. We know that each piece of the ring is going to be affecting our point here, right? So we have this red piece here from this ring. It's going to have a vector that points both down radially, right? Because this is R. And it's also going to have a piece that points along the z-axis. See, there's two components of that electric field at point P over here. Now, at the same time, we could have this green point. Let's see if I can actually zoom in. Yeah. Okay. We could have this green point also interacting or at least causing a field over here, an electric field at point P. Now you'll notice that how much ever is in the radial direction is going to be the same uh, all the way around. So it's going to cancel. So here you'll see that the component of this vector that's pointing out radially, let's mark it in blue. This component from this green piece is pointing radially, essentially in the opposite direction as this component from the red piece. Okay, so these two vectors are going to cancel each other out. The only thing left over is the along z-axis components of these two vectors. Okay, so there is our argument from symmetry. Now, something else to remember, even though the mathematics just got so much easier because we're using this radial symmetric argument, um, we do have a charged surface. So we're going to use eta equals the total charge, Q of the whole disk, divided by the area of the whole disk, which is just pi r squared. Okay? So now we've got pretty much all the information we needed from the picture, from the pictorial representation, and we can move on and actually start thinking about setting this up mathematically. Now, we know we have essentially kq over r squared because that's the electric field in its most basic form, right? So here's my k, but we're considering those thin rings, remember? We've got these rings we're considering. Okay, so we're not thinking about the whole charge right now. We're just thinking about this little ring of charge, which is delta Q. Okay, so if we think about a particular ring I, we can number these, right? Out from the center of the circle outward, 1, 2, 3, 4, 5, and so on. So if we just think about some random one, we're going to call it I. Well, it's going to have some piece of that total charge Q, so we're just going to call it delta Q. We know that all the points on that ring are all going to be the same distance away from point P. That's just because of symmetry. So this R and this R, R1, R2, these R's are the same. So we can use that to our advantage. We can just say, well, each of these individual rings are going to be essentially the same distance away. And then we need to include that cosine theta component, because remember, we've got these vectors that look like this. We want the adjacent piece. So I'll draw that here. We want this adjacent piece, which is going to be a cosine theta. Let's see, this is actually the z-axis. So we want that z-axis component. So we need to throw in the cosine there. Well, that's all well and good, but we still have some work to do because we have this r, we have this cosine theta. We want to rewrite those in terms of something we can integrate across the disk. Now, just looking at how this is set up, it looks like we want to integrate. Again, that's not real mathematical notation, just shorthand, but it looks like we want to integrate across the radius from the midpoint to the end of this ring. But we need to include a few things here because we don't have an R here. Um, so let's think about how we can rewrite this thing. Now here's the trap that I want to highlight. So we need to be careful. Notice that This r is this distance here, but we can do a subtle rewriting, okay? So this is what's going to happen. You need to watch out for this. So this is the distance we want. We want the thing in blue, right? We want the blue length, but we want to integrate across the radius of the ring. So we want to integrate this way, but right now we have this blue piece. So let's rewrite this. We know this blue Ri, the long hypotenuse piece, can actually be rewritten just using the Pythagorean theorem. You can actually rewrite this as the orange uh, radius of the circle, which is here, right? I'm going to draw over that again. And then that's one piece of the triangle. And then we also have this piece here, this Z piece, right? So here's the rub. Here's what you got to watch out for. We have this blue R and we have this orange R. I could have thrown in another variable and it'd be really confusing, but this highlights the issue of when you start talking about distances and you're using circular coordinates like this, like polar coordinates or cylindrical coordinates, you have to be careful and keep up with what your R's are. Okay, so we're going to rewrite this blue R. This blue R gets rewritten to include the Pythagorean theorem orange R. So you see what I did there? I just plugged in the Pythagorean theorem version of our blue distance from the picture. Now I just need to rewrite cosine theta. That's also just adjacent over the hypotenuse. So that's going to be the adjacent piece over the hypotenuse, which is the wait, sorry, hold on. The adjacent piece over the hypotenuse. There we go. So this term here, that's just our cosine theta. Now we can simplify the denominator because these are similar, and that gives us this final term. So all that being said, where we plugged in things, how we got there, the contribution of the individual rings can be summed up like this. Okay, so that's just one ring, then we add across all of them. Give me one moment. Here we go. Okay. Now the next problem is we have this integration across physical dimensions. Let me switch back to red. Okay, remember we wanted to integrate across the radius r. We want to add up these individual rings, but we still have this pesky delta Q, right? This is saying, oh, we have individual charges. Let's add up the charges. We don't want to do that. We want to add up across R. Okay, well, we can sort of get at that. We can go back to our surface charge density, okay, which was just that eta equals delta Q over delta A. Remember, we can use the total Q over total A or divide it up into those chunks and have a little piece of Q divided by a little piece of A, okay? So the total charges of each ring can be represented essentially as this. So here's our delta Q equals eta times delta A. So that's just the charge from an individual ring. Now, if you consider that the area of a ring, if we take this ring and just snap it apart, we can stretch it out into a rectangle. You'll see that's happened right here in the figure. They just take this ring, they lay it out flat, and it turns out um, we can think about the area of this thing as just having a length of 2 pi r, right? Because that was the circumference that was broken down into the side of the ring. And then it's going to have a width or a little bit of a depth radially outward. So we have the 2 pi r, then it's going to have the depth of just this tiny little baby sliver delta r. So it turns out we can actually rewrite the little sliver of area as just the length times the width of this rectangle. And it's still the same area as that ring. We just snapped it apart. All right. Now let's put all this together. So this is what we derived from that pesky which are we talking about? Because one was the distance, because that's the notation. The other one was the radius of the ring or the radius of the disk. So now we know what we're talking about. We have the distance from our point. This is now the radius of the ring because we did that, or the radius outward to the ring, the radius of the disk. Um, we took care of that transformation, and now we can rewrite this individual charge of the ring as just eta times uh, that piece of area that it corresponds to. All right. Now remember that from the previous slide, no, we're not to the infinitesimals yet. Let's change that back to a delta R. So I'm going to plug in this for A. Okay. So you'll notice if we compare these outside terms, I've plugged in the 2 pi R delta R, and I've let things cancel out. Okay. No big deal there. The only thing left over in the numerator is the Ri delta R. Now we can finally start summing across these rings. So what we want to do is we want to let these thin rings get infinitely thin, right? We want to make them so tiny that they sort of collapse on themselves into, I don't want to say point rings, but just very thin rings, okay? And we all know from Calc 2 what's going to happen is when we let this delta R get infinitesimally small, it will become a differential. And then the summation will become an integral. Now, remember earlier I said we want to integrate across the physical feature of the object. So we're going to integrate from the center of the circle. I'm going to draw this in blue. The center of the circle up to the full radius of the circle. So we're going to work our way outward, adding up all these super, super thin rings. But this integral sort of looks gross, right? Because we're integrating over this function. Our variable is here, our variable is here. It looks gross. Again, if you want to look this up in like Shams, if you want to be old school, like when I was an undergrad, you could just flip through integral table. Otherwise, you could use Wolfram Alpha or something like that. So we're going to go through and integrate this. Spoiler alert, you need a U substitution to make this happen, okay? So just bringing this along for the ride from the previous slide. So that's just from our previous slide. What we're going to do is we're just going to set U equal to the crap in the denominator under that 2/3 root. Okay. Now I'm sure you guys remember how to do the whole like if U equals this, then you do the du, all that jazz. I will not go through these steps because that is something you should be able to do on your own. You should be able to get from here to here. You should be able to set up a U substitution. But essentially, once you get this U substitution set up, remember to change your limits, okay? So remember, we're letting R go from 0 to big R. So that means U is going to be z squared plus, well, our first limit is 0. Okay, so our lower limit is just z squared. That's where this one comes from. Then the next time we just plug in the big R. So U is going to be z squared plus big R squared, because that's their new limits, what we're letting R do, right? So R goes from 0 to big R. That's where those limits come from. So once you do that and you integrate, Okay, you get to this step here. It looks a little gross. Again, use substitution, something you should be able to do. And then you essentially just do your B minus A to evaluate this definite integral. And then you get these two terms that pop out with these coefficients out front. Now, for one more step, what I'm going to do is I'm going to distribute this Z. I'm going to distribute this Z through both terms. And here's my final answer. Okay, so that was a whole lot of work for just one piece of a parallel plate capacitor. Remember, this is just for one disk. Do note that this is only for positive Z. If we wanted to go in the negative direction, we have to we have to negate this value. So if this is our parallel plate capacitor and this is Z, all the math we did was for some point over here. If we wanted to figure out, we'll call this P prime, if we want to figure out the electric field over here on this other side, remember we have to put that negative sign in front of it. All right. Um, so usually in a parallel plate capacitor, the plates are very close together. We're talking like super close, okay? So when they're close together, the distance away from one plate will always be small. So if you're thinking of some particle in here, in this picture, um, your distance from the plate, so it's always going to be a little tiny distance away. Now, just like in the last lecture, we talked about if you have a relatively large plate compared to a charged particle, and you're sort of inside the plate, you can actually treat the plate like it's an infinite charged plane. And that's exactly what we're going to do. So in this case, we're just going to say, because the circular plates are easier, but the idea works for square plates as well. So in this case, we're going to let R just explode, and we're going to say, like, compared to our distance away from the plate, R is going to be huge. Um, and this actually is fairly easy to do. So we have our original statement from the previous slide. We let R go to infinity, and look at what happens here. So I just pull out my component, big deal, my coefficient. Then I let R get huge, which means, yes, sorry, I had to think about that for a second. Um, so if we let R get huge, pretty much this whole term goes away. And then we're just left with this coefficient times 1. That's nice and easy. Okay, so we're left with this being our electric field. Okay, so here's our electric field of a large plane. Notice that, again, we have to make sure we know if we need to add the positive sign or the negative sign. So if we're a positive distance away from the plane and the plane is positively charged, we get the plus sign. If it's we're on the other side, we have to dump in that negative sign. What's really strange is, and this is important, the E field is not dependent on distance. Remember how we said that E fields, remember how we said E fields drop off as you get away? Look, there's no Z in the math, right? There's just the Z over here that tells us if we're going to be on the positive side or the negative side of this thing. But look at the mathematics itself. You cannot plug in a distance and make the electric field smaller. It's just eta over 2 epsilon naught everywhere. That is everywhere inside a capacitor. So no matter if you're super close or a little bit further away or almost closer to the other plate in a parallel plate capacitor, you essentially get the same electric field. It doesn't decay as you get further away. That's a little freaky, I think. But let's explore this idea of putting something inside of a parallel plate capacitor. All right, so in a capacitor, obviously we have two plates, even though we did the math for one. We have two plates. We have this positive one and we have this negative one. They're parallel and of equal strength. That's important. So now we can talk about the superposition. Okay, their superposition of their fields will create a net electric field inside the capacitor. And this is going to point to the positive plate um, to the negative plate. And so from the positive to the negative. That makes sense. Positive E fields point outward, negative E fields point inward. Okay. Um, and we can think about this uh, under the assumption that these plates are infinitely charged planes. So let's see what happens here. All right. So I'm going to start with let's look at the electric fields of this positive plate. Okay. So remember, positive radiates outward. So that's the positive component coming from this plate. We also have the positive electric field over here. We also have the positive over here because that's still coming from the positive plate. Notice how they're all the same size. So the E field is all the same size. That's because we just showed from an infinite plate your field doesn't decay, it doesn't get weaker with distance. So all these are going to be, as long as you're close to the parallel plate capacitor, they're going to be the same. Now let's look at ooh, let's look at this other plate. We'll do the negative one in green. Right? Well, we know over here we're going to feel some of that electric field going toward the negative plate. Inside, we're also going to have a field going toward the negative plate. And outside, we're going to have a field going toward the negative plate. Remember, they're equal strength but opposite directions. So these are going to cancel out. These cancel out. Okay, so it looks like there's no field outside of the plate. However, look at what happens on the inside. Only on the inside do you have two electric fields of the same strength pointing in the same direction. So that means you just get two of these pointing in the same direction inside, in between the plates. So you essentially, from one E to the other, you get double E inside the plate. Okay, so I've notated that here. Inside the capacitor, you essentially get twice the electric field from one of them because they double up. And if we plug this in and do the math, it turns out for any capacitor at all, it's just the charge density divided by the permittivity of free space, the epsilon naught. Now we can also plug in that surface charge density because we want to get those characteristics of the plate. We want to get the Q and the A back in there so we can actually represent this in terms of the characteristics of the plate. So it turns out your electric field really just depends on how charged something is and how big it is. This is for a parallel plate capacitor though. Yeah, a PP cap. Okay, so this is for a PP cap. Q divided by A is going to essentially tell you everything you need to know about that electric field inside. You remember back when we had the electrostatic constant, which was just K, and I said sometimes it's easier to rewrite it as 1 over 4 pi epsilon naught. And I'm sure some of you were like, that's so many things. Why is that easier? This is why. situations like this where the 4 pi just goes away and you're left with just E epsilon naught. You're just left with that permittivity constant. See, if we'd kept it in terms of K, we'd have so many other things floating around. Um, right, so let's talk about these uniform electric fields. Obviously, no real capacitor is infinite, but this idea of an infinite parallel plate capacitor is a really good approximation. And as you probably figured out by now, that's what physics is all about, is really good approximations. Um, this you could pretty much use in all cases if the separation distance of the capacitor is small, right? So if our separation distance, which is this, is tiny, this little approximation is going to do just fine. Um, Weak fields do get generated outside of the capacitor. These are called fringe fields. So if you look at what's going on outside of a real capacitor, you're going to get some really weak fields on the outside. You're going to have some edge effects. A lot of times they're so weak you can just ignore them, unless you're making something like super sensitive, really small, super sensitive, where the capacitors around a lot of other electronic components. Um, Other than that, you should be fine with just approximation. And if I haven't actually said this, I think I did, but if not, when an electric field is the same strength and direction at every point in a region of space, this is a uniform electric field. So you can see that's clearly what's happening in between these two parallel plate capacitors. Now, if we put a charged particle inside this uniform electric field, it will experience a force. Remember, we have a Q inside an E field. We get F equals QE. We drop a charged particle in here. So if this is Q, let's say it's positive Q. Well, it's really close to this positive plate, which means it's going to feel a force. It doesn't want to be near the positive plate because it's also a positive charge. So it's going to ride along this electric field, the thing that's going to drive and carry this force, and it's going to want to move away. So the moral of the story here is if you have an electric field like this one, your positive charge is going to experience a force in the direction of the E field, but a negative charge will experience a force in the opposite direction. So had we come up here and dropped in a negative charge Q, obviously it's the same as the negative charges on the plate on the right. So it's going to travel against the grain, so to speak, and go in the opposite direction of the electric field. Now we can actually talk about the motion of these particles and calculate what's going to happen. So if you have a particle Q at rest, and then it suddenly experiences this force, this QE force, well, then Newton's second law is going to take over. So you'll remember from physics 1, Newton's second law is F equals ma, but that F is actually from the electric field. So we get ma equals QE, right? So here's Newton's second law. Here's the E field that's acting, and we can actually solve for the acceleration. Just divide both sides by m essentially. Now this ratio that comes out, this Q over m ratio, that's actually called the charged mass ratio. And a lot of times when you're talking about particles moving in fields, you talk about their charge to mass ratio, not just their charge or just their mass. So it's important to note that you could have two very different particles with two different charges, different Q's, different masses. But when you calculate the ratios for each particle, they could have the same charge to mass ratio. So you could have something like a charge of 1 over a mass of 2, and then a charge of 2 over a mass of 4. That's the same charge to mass ratio, which means that even though one particle is twice as big as the other, they will undergo the same acceleration and follow the same trajectory because their Q to M ratio is the same. All right. And in situations where you have a nice uniform electric field, um, a particle is going to move with constant acceleration. Now ask yourself, where have we seen constant acceleration before? And the answer is free fall. When you're really close to the Earth, gravity we pretty much just say is 9.8 meters per second squared. Well, that's constant. That's kind of a uniform gravitational field, right? So you can think of a uniform electric field sort of like a body in free fall with this constant accelerating force. It's not gravity. It's these particles are so small, we don't worry about gravity. So we're just going to think about the electric field as sort of like this different kind of gravitational field that's going to move these particles. But it's important to remember this is a uniform electric field that we're talking about. Uh, Again, for small things like atoms, protons, electrons, you can ignore the influence of gravity. You don't have to include that when you're doing problems and things like that. So the basic trajectory of this charged particle, or any charged particle in a uniform electric field, is a parabola, just like free fall. Remember, free fall was always a parabolic shape. Same thing here. Um, So if the charged particle moves parallel to the electric field vectors, the motion is one-dimensional, just like in free fall. And then if it moves perpendicular, you start getting some other features, just like if in projectile motion. Okay. And this is actually the basic idea of an electron gun. So an electron gun, back in the day, those big TVs, which some of you may not even remember, or the big white computer monitors, they actually had these cathode ray tube things in them. And what these cathode ray tubes would do is they would actually shoot electrons at the screen, and electrons would be shot at different energies. Actually, I should draw this. So here's your computer monitor, and you're looking at it. So the electron gun would actually bombard the screen with electrons, and depending on the energy of the electrons, it would cause the different colors that you would see while you're watching TV. And the whole idea of an electron gun is right here. So what happens is you have an electron. I'm going to switch to blue for this. I don't know why, but every textbook ever always makes electrons blue. Okay, so you have this electron is coming in. Notice that it's a straight path, and it's got some sort of velocity. It's coming in perpendicular to the field, which means it's not going to be a straight across problem. That's parallel. This is going to be perpendicular, so we're going to get a parabola. So you'll notice it starts accelerating toward the positive charge, right? Because the electron wants to go to the positive charges. So then you get this parabolic shape. Now, something to think about is you can actually, and this will be important for a particular problem set question, as this thing leaves, you can calculate how much has been shifted off of its original path, right? Because If the electric field wasn't there, it would just continue straight. But it's been shifted. I should probably draw this better. There we go. You can calculate. I bet I can erase this now. Nope. Okay, so you can calculate that deflection in the electric field and notice once it leaves the electric field, it's a straight line again. But it's got a different angle, right? It was coming in just right along the x-axis. Now it's coming out at a different angle. It's been shifted from that x-axis, but it's at least traveling in a straight line again. So if you were to think about it, you could do the math to figure out where on some screen it would hit if you were thinking about like a computer monitor or the backside of a computer monitor. Now, that's a point charge. What about something a little more complicated inside an electric field? So it turns out if we want to think about dipoles, since we know what those are now, we can actually take a dipole and think about what's going to happen to it in a uniform electric field. What's really weird is there's no net force on a dipole in a uniform electric field, but the electric field does affect the dipole. So how can an effect happen? How can an effect happen without a net force? And that's an interesting question. Um, so there are two forces that act on a dipole. They're not aligned with each other. So these two unaligned forces, why am I throwing up balloons? Okay, so there are two forces not aligned with each other. The electric field will actually cause those to torque, even though they're equal and opposite. Since they're not coming from the same point, you're going to get a torque on the dipole, and that's going to cause a rotation. And you can see that here. So you'll have from the negative side of the dipole is going to go in the opposite direction of the E field. Uh, Positive part of the dipole wants to go with the E field. You see how it's going to pull these apart and rotate this thing? It's going to reduce that angle to 0. But you'll notice that both of these forces, this force and this force, if you add those up, you get 0 newtons because they're equal and opposite, but because they're offset, that's where you get the rotation. So that answers the question how you can affect a dipole without a net force. Of course, this will cause the dipole to rotate until it reaches this equilibrium position, and this is the ideas behind polarization. You can polarize a dipole by applying an electric field to it. So here you can see a bunch of dipoles placed into an electric field, and then you get this nice, pretty no net force, equal opposite canceling out alignment of these dipoles inside the electric field. Now, in a non-uniform electric field, it makes sense that the net force on a dipole is actually toward the direction of the strongest field. So any sort of finite size charge, as soon as you stop using uh, that infinite sheet or infinite line approximation, as soon as you say, okay, this object has a definite size, then you sort of lose your uniform electric field. So in more real world cases, maybe the dipole and the particle are similar in size. Um, that's when you get an actual net force occurring on a dipole. And as you might expect, if you have a positive charge, you'll have your E field pointing out, which will cause your negative part of the dipole to travel in the opposite direction of the electric field toward that charge. And then on the other hand, if you have a negative charge, your electric field, of course, will point inward. which will cause your positive charge to want to go in the direction of the E field toward the negative source charge. All right, so that's pretty much everything for electric fields. The next logical step in this will be going from here to Gauss's law. And Gauss's law is essentially a way that we can use some fancy calculus and in some cases some multivariable calculus to take an object with a charge, draw this theoretical mathematical shape around it, and then look at how much electric field is going through this theoretical mathematical shape. So get ready, buckle up. The math is going to get fun in Gauss's law as we start moving up on that, but we are still in the realm of talking about electric fields. We did talk about your first electrical component. So remember um, the parallel plate capacitor for those of you that want to take an electronics course, or if you want to transfer from here and do a degree in electrical engineering. This is something that you'll be using a lot in your lab-based classes. So make sure you understand uh, the concepts here of what's going on with the electric fields inside of these parallel plate capacitors.